Where were you again? And who's your fitness teacher at Stanford? Oh, yeah. I like Stanford. It's a good school. No? Oh, I like Stanford.
School, like the people there.
Like students or staff? Is it? Oh, I'm sorry to hear that.
Staff, but most.
Some staff. Well, fair enough. Well, I'll have to see what you think about Eastdale once you've been here a bit.
I think
Listen, I've taught at 11 schools at the SBI and Eastdale's my favorite. I like it a lot. Have you been to a lot? Do you move around a lot?
Yeah.
Or are you like knifing people and getting kicked out? Like, what's going on here?
Well, okay.
Oh gosh, I thought I was just joking, but
No, I got kicked out.
Did you?
But not for like.
Oh, we'll share
For
later.
the stupidest reason.
Listen, I have to get into this, but I am nosy. I want to hear this later. All right?
Okay.
All right, guys, let's get to it. I just want to point out again, I created this example a while ago. And then look how appropriate it is for today. It's so well chosen. But we're going to have to make a change. King. And is it Charles III? Do I have that right? Is he the third Charles? Yeah.
Yes, he's the third.
So there we go. So how quickly things change. So from King George VI to Queen Elizabeth II to King Charles III. So in biology, when we get talking about species, if we accept the premise, and we will talk later on in this course of why we should accept this premise, if we accept the premise that the species that are on Earth now came to be by changes in species that used to be on Earth, if we accept the premise that evolution has happened and that's where the current species we have come from, and we're going to talk about why we believe that later on, then we have to understand that if you want to know about the species that are on Earth right now, we have to look at the species that were on Earth in the past. Does that make sense? That the way we have new, different living things now is that over time, as individuals had offspring, those offspring were a little different than they were. And that if you repeat that process for literally billions of years, you end up with a great variety of different living things. Does that make sense? I mean, look how different humans are, and they've only had a few thousand, maybe 100,000 years to procreate, which in evolutionary terms, in terms of biology, is just the blink of an eye. It's just barely any time at all. Does that make sense? And even still, we have people of different shapes and sizes and heights, and different skills and different talents and different builds, and different, physical characteristics and different pigmentation, all these differences, and humans have barely had any time to evolve and change at all, because we just have not been on Earth very long. Does that make sense? So to understand the present, we have to look at the past. So if we're going to look at the past, we're going to be looking at sort of family trees. Now, I chose this family tree because it's sort of a famous one and one that people can wrap their head around pretty easily. And I want to use this family tree to kind of give us some terminology to work with. And so the first thing I'm going to say is if you want to understand your own genetics, if you want to understand your own systems, where your own kind of existence comes from, it's important to understand all of our ancestors, which raises a question. What's an ancestor? So, what's an ancestor? Yeah.
Someone that has come before you.
Okay, good. Someone who has come before me. Now, does that mean that all the dinosaurs are my ancestors because they came before me? Or like Elvis? Is Elvis my ancestor?
Related to you.
Related to me. So an ancestor is somebody who came before me who is related to me. So now we get to a better question. Is my Uncle Robert, who's a bit of a character, is he my ancestor? Or is he just an old guy in my family? Is my uncle my ancestor?
But is your uncle your ancestor? Yes.
Yeah.
If he's older than you.
Okay, and so here we,
To be an ancestor, first they have to be dead.
they have to be dead?
No.
I don't know.
My dad's my ancestor.
Well, there's an interesting thing, and I think this is,
Or wait.
This is actually perfect because this is what happens often in science, which is we're bumping into the way we use a word in day-to-day life with the way scientists use a word. Does that make sense? And they're definitely similar, but they're not quite identical. And so I like this debate because the answer is, I think if we're talking like humans and talking like your history, we'd probably agree that your ancestors are the people who like used to be around and have died, right? In biological terms, an ancestor, you hit most of the key points. Is somebody related to you, somebody in your family tree? But it's more than that. My uncle wouldn't count biologically speaking as my ancestor because even though he is related to me, I'm not a part of his direct line. Does that make sense? In other words, a way to think of an ancestor is, like Back to the Future? Everyone seen Back to the Future? It's a perfect movie. It's a great movie. Okay, so you go back in time and then you like accidentally, if you actually think about Back to the Future, it's a very creepy film, right? Like goes back in time and then like his mother falls in love with him. And then because his mother is falling in love with him, she like almost doesn't fall in love with his father. And so like he starts like going like half visible and like can't play the guitar anymore. Listen, watch the movie. That's what happened. But the reason is, if you take one of your ancestors out of your family tree, what happens to you?
You're gone.
You're gone. You're out of there.
So it's like people that have helped like create you.
Bingo. Very good. So that's how I want you to think of an ancestor. An ancestor is any individual back throughout all of history where if you take them out of the equation, you aren't possible because you have descended directly from them. Does that make sense? You take my uncle out of the picture, I'd be sad to lose Rob because he's a character, but like I'd still be here. But you take his brother, who is my dad, out of the picture, I can't be here, right? Because my dad had to be there for me to be here. Is that a fairly clear definition? Great. Now we're going to write one that isn't clear at all because it's going to be like a sentence which is way more confusing. An individual from whom you are directly descended is your ancestor. I think I'm almost back, ancestor. I think I'm almost back to school writing. I'm getting neat again. Tuesday was bad, man. It was squirrely. Yeah. 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 We just need to get like a nice projector set up for her and clean it up. It sucks. Like, it's nothing like, it's just kind of leftover stuff. Yeah. Yeah, she knows it. She okayed it. Yeah. Yeah, no, she needs it. Yep.
I used to read. I'd sit there and write like notes or whatever, but I don't know.
I don't know if you all saw that, but I've been cashing checks with other departments' budgets, and Matola's just coming to check in on me. I just ordered a bunch of computer stuff this week, but I was like, bill this to music, bill this to English. He doesn't trust me. I trust me. This is what I'm saying. I'm not.
He doesn't trust me, but I trust me. Of course you trust yourself.
No, listen. I don't know. I don't always trust me, but that's not true, right? Like, listen, if I'm going for heart surgery, I don't trust me. I want the doctor. If I'm getting my car fixed, I want the mechanic. But it depends on the thing. Is all I'm saying. All right. So now, let's just test this really quickly. I want you to tell me 3 people who are Prince William's ancestors and 2 people who aren't. All right? Write them down. I want you just on the side, just scribble 3 names. We're looking at William, and we're going to play a little game of ancestor or not, just to make sure we have the principle of this down. For William, the Duke of Cambridge, I wonder if his title's changed now. How does that work? See, I don't understand these things. I need to do some reading. I want to know 3 people who are his ancestors and 2 people who are not his ancestors. Write it down.
That's it. Her son or her grandson?
Wait, is it? No, it's her grandson. It's her grandson. So.
Okay, so Princess Margaret's Well, it's not. Wait, did he say related or ancestor?
Ancestor.
Okay, so we go with Prince Edward, and Prince Andrew. Pretty much any of those princes were not related, and then Queen Elizabeth and Prince Philip were related. Or ancestors. I mean, you know.
You good? Cool. All right, who wants to give me not an ancestor? Who can tell me somebody who is definitely not Prince William's ancestor? Yeah.
Prince Edward.
All right, so we look at Edward, and we say that even though Edward is definitely related to William, what would Edward be to William, by the way? What is that relationship? Because William's dad appears to be Charles, so this would be his uncle. Very good. So Edward is not. Very good. All right, who wants to give me somebody who definitely is his ancestor? Yeah, Natalia. Yeah, Diana. Who's Diana to him? His mom, yeah, mother. Very good. So Diana is. Somebody else who is? Yeah, Tatiana. Yeah. Someone else who isn't. Lots to choose from here. Yeah. Anne. Princess Anne. That's right. We're sticking with aunts and uncles here, I see. Who else isn't an ancestor? I mean, you could say, obviously, anyone like Archie. Archie's not his ancestor. I just like saying Archie, so I'm going to write that down. Who else is an ancestor? Let's choose from. Yeah. Yeah, sure. Yeah, very good. All the way back to George.
That is the ancestor. Why?
Because it's his mom.
That's his mom.
Yeah, so Camilla is wife number 2.
That's such a confusing little trick then.
I know, isn't it? Yeah, so Charles and Diana, it's like a lot of people's family trees, right? Like this.
I've got 5 siblings on my mom.
Some people's family trees are very linear, and some people's family trees are very, very branchy. And you know what? They're both good trees. It's just how it goes. Yeah, that's right. As long as it casts some shade. All right. Does that make sense? Can somebody name somebody on here who has no ancestors on this family tree? Yeah.
King George and Queen Elizabeth, neither of them have ancestors on the family.
Very good, yeah. These guys don't have ancestors on here because they're right at the top, right? Obviously, do they have ancestors in real life?
Sure.
Of course, but none on this tree. Who else? Yeah. Yeah, Meghan, Duchess of Sussex, though I believe she is no longer the Duchess of Sussex. I think this picture's out of date. Did they not abdicate their... I don't know. I don't know how these things work. I don't really know much about the royal family in the interest of full disclosure.
People are still calling them Duchess.
Yeah.
So I don't know exactly.
But anyway, yeah, she has no ancestors. She's married into this family, so none of these people are her ancestors. Yeah.
Amelia.
Yeah, very good. Camilla Parker Bowles, the Duchess of Cornwall, does not have any ancestors on here. Good. Yeah. Yeah, exactly. So you guys get it. We get the idea. The reason this is important is because we're going to talk a lot in this course about species that have common ancestors, which means that somewhere in the past, humans and every other living thing on Earth, there's some organism back there that was an ancestor to both of us. This is predicated on the assumption that it may well be the case that when cells first came to exist, on Earth at first, there was probably one of them. Does that make sense? And that divided, and it kept having offsprings. So if you go far enough back, you're related to every other animal on Earth, to some kind of common ancestor. Now, with some of them, by the way, that is like people. You are, if you go back far enough, related to every human on Earth. For some of us, we have to go very far back, and for some of us, you don't have to go very far back. But you are related to every other human on Earth, because if you go back far enough, you will find an ancestor that was ancestor to everyone. This, by the way, this should serve as encouragement of a sort, There's nobody all that different. So, with that in mind, I would just want to switch to the next page. What does it mean to evolve?
To adapt to your environment over a long period of time.
Yeah, very good. Species will undergo small changes over time. With enough time, small changes add up to big changes. Does that make sense? That's kind of a weird sentence. And I'm sure that any other science teacher looking at this would be like, that's an embarrassing and humiliating sentence. But I think it's actually good. I think it actually says what I mean for it to say.
I know that elephants are actually evolving to not have tusks.
Yeah. Yeah, this is a prime example, which elephants that have big, long tusks have been so hunted that largely the only elephants surviving to procreate are those with small, not very attractive to poachers' tusks, or none at all. And so over time, we are seeing, and there's an example of evolution happening on a really shortened time frame, which is happening because humans are terrible and like to kill things, like in huge numbers. So with enough time, the small changes that can happen can add up to big ones, and eventually these changes can actually lead to ending up with a species, an organism that's so different from what it started as, it's a new species. Yeah, of course. You don't have to ask me that, by the way. I trust all of you to manage your own bodily functions without my help or input. And frankly, like, if I were 17 years old and said, can I go to the bathroom? And some 38-year-old guy was like, no, I'd be like, I think I'm still going.
Yeah, that
So-
happened to me last year.
so-
I was like, I'm sorry.
So you can,
She's gonna use this man's strength.
I'm very strong.
I'm very strong.
I know, it's the first thing people notice about me. I can't help it. I'm very physically intimidating.
Everyone.
And eventually, if these changes become big enough, you can actually get an individual that is no longer compatible with, its ancestors that it changed from. And that is when we would say you have a new species that has come to be. Does that make sense? Eventually, you think dogs and wolves come from a common ancestor. At one time, they're the same species, and changes happened over time. And now you have two species, wolves and dogs, neither of which is the original species. That original species isn't here anymore. It has changed over time. But some of the ones over here changed in one way. Some of the ones that were living over here changed in a different way. And from one species that is no more, you now have two existent species that are different from one another and different from what came before. And that's how species form. And when we talk about evolution, that's what we're talking about. We're talking about small changes adding up to the point where we have a whole new species, where what exists today is a different thing than what existed in the past. And this process can't be stopped. By the very nature of sexual reproduction, it means that every offspring is different from its parents. And so over time, changes occur. And eventually, if you looked at a human today and a human 200,000 years ago, you would see differences. Already you would look and say, there are things very different between modern humans and those. And again, in evolutionary terms, 200,000 years is just so little time. Remember, the Earth has been around for not thousands of years, not tens of thousands, not hundreds of thousands, not millions, but billions with a B of years. And that is a long time. It's hard to think about how long that is. Yeah?
Aren't humans sort of a long time ago, like super short?
Not all of them. There are other hominids, like other human species that I believe were even taller than us, though humans, Homo sapiens like us, have been steadily growing taller throughout human history, even as recently as if you go to Fort George and look at the real uniforms that soldiers wore in 1812, like most of these guys are like between 5'3" and 5'8". They look like my dad. My dad's 5'4". He's a little guy. He's also like jacked, but we don't talk about that. He's just much shorter than I am. Yeah. And this is a change, which also means like just over time we see changes. And there's nothing to say that that change won't reverse itself.
Excuse the interruption.
Yeah. Yeah.
Quiet roost with you.
Yeah.
Come to guidance, please.
Yeah. Guidance? Is that Wyatt Roost to guidance? Wyatt, they want you in guidance. See, I can hear. It's good. It works. Okay. So, I don't think so. I think you'll be back. So let's talk then what this means. We can say we have a shared evolutionary history, which means the job of modern taxonomy, the job of that kingdom, phylum, class, order, family, genus, species that we're talking about, is to figure out how recently you have a common ancestor with other species. If you have an ancestor commonly with another species only a couple million years back, you are very closely related. Whereas if you have to go back 3 billion years to find a common ancestor, like us and bacteria, well, then you are very distantly related. How closely your common ancestor is gives you a sense of how related you are, right? This is no different than like the difference between a first cousin and a fourth cousin. Oh, our parents were siblings versus, like our grandparents were cousins. Does that make sense? It tells you, if you figure out how recently there's somebody who's an ancestor to both of you, you know how closely related you are. Did that sentence make any kind of sense?
You lost me.
I lost me as I was saying it, if I'm being completely honest. But I think drawing the picture will help. So how do we do this? There's 3 ways that we can look to see how closely related different species are. And this is going to sound familiar because it relates to what we talked about yesterday. The first thing we can do is we can look at anatomy. Does anyone want to guess for me what species we're looking at here? We're looking at 4 different species of animals that are all quite closely related. Does anyone know what they are? Yeah.
I'm guessing there's winged species or mammals.
These are all mammals. Very good. Does anyone know? Somebody said this is a bat. That's correct. So that is the wing of a bat. Does anyone have any guesses on the other ones? Yeah. Human. Good guess with ape, but no, actually. Think closer to home. I want you to look really closely at these structures. They should be a giveaway. Close? Cat. Very good. That is the forelimb of a human, right? The arms of a human. This is the forelimb of a cat. So the 2 front paws of a cat. Hey, anyone, real quick, is that a right forelimb or a left forelimb that we're looking at?
Left because it's on the inside.
This claw, is that claw not usually on the outside with a cat? Or is it on the inside?
It's on the inside.
It's on the inside? Then this would be left. Yeah, good. Whereas this one here, we're looking at the front. So if we're looking at the front, it would be like this one here. So that would be a left arm as well for a human. I wonder if they're all left. Probably. Cool. So that's me asking a question I don't know the answer to. You're not supposed to do that. But we figured it out. What's this? Does anyone know? Ooh. Good. Very good. And it's a mammal. So a mammal with a fin. What are we talking about, probably? Good guess. It's the other one, but those are the 2 reasonable guesses. This is, in fact, a whale. In fact, this is a blue whale, but we'll just say a whale. Now, here's what I want you to look at. One of the ways we know that these things are related is, I would like to point out something to you. Can we talk about the fact that a whale has a wrist with all the same bones as your wrist. It has an upper arm, just like you have an upper arm. It has a lower arm with 2 bones, just like you. You know that you have, what's this bone called? Big guy. Nope, that's in the leg. No, listen, that's a good guess. That's the leg. For the arm, funny bone, it's the humerus. All right? Humerus, and then you've got 2 bones down here. What are they called? Anyone? Radius and ulna. Anyone heard that before? Yeah. Radius and ulna. And radius and ulna are cool because as you supinate and pronate your wrist, they cross over each other. Feel it. Put your hands on here, rotate your wrist, and you'll feel that they cross over each other and then cross back. Feel it. Right now they're parallel to each other. So if you pronate your hand, if you have your palm facing down, your radius and your ulna run parallel to each other. And now, supinate your hand, which means to leave your arm where it is, but rotate your forearm. And for your body to do that, those two bones have to cross over each other, which I find gross and creepy every time I think about it. Can you feel it? They make an X. And then they straighten back up. Isn't that cool? And that structure, you have a muscle that pulls one over the other right here, and that's what allows you to pronate and supinate your wrist. If your bones couldn't do that, your wrist would be stuck like this, and if you wanted to pick something up, like you can imagine, without the ability to rotate your wrist, it would be hard work to draw, right? Oh, well, now I've really screwed things up. So there we are. Now, here's the crazy thing. Your cat, does it pronate and supinate its wrist?
No. Sure.
Go home and pay attention. Who has cats?
Wait, how would that?
I want you to go home and pay attention. Find out for me. Can it lift and go palm up or not? Find out. Does a whale do that? Are these two bones going to cross over each other? And yet it has the two bones. It has the bones to do that, even though it doesn't do it. What about a bat? They rotate their wings a lot. Maybe. I don't know. It actually looks to me like these are fused, so I don't think so, but I'm not sure. But here's the point. We all have those two bones, even though some of us use them and some of them don't. And then let's note, okay, fingers and a thumb. That makes sense. Fingers and a thumb, the exact same set of bones, the exact same number, the exact same, right? Like hamate, pisiform, scaphoid, lunate, can't remember. And then 5 fingers, which have proximal, distal, middle, and proximal, middle, and distal phalanges. That's what you call the fingers. These are called the metacarpal bones. We have those in a human. Your cat has the exact same set of bones. They're a different shape, but they have all the exact same bones. A whale has all the exact same bones, despite the fact that they don't have arms or hands. It's just making a flipper. But nature has designed them, or they have evolved, to be based on the exact same system of bones. They don't have different bones. They just built a different structure around it. And then a bat, look at this, the exact same bones, despite the fact that it's not an arm, there's no fingers, it's just a wing, but it's a variation on the body plan. And you know what I think it's like? You know when you're designing your character in a video game and you can like move the sliders and make them taller, make them shorter, make the head bigger, make the head smaller, make the face rounder, make the face more narrow? It's all the same parts and you can just adjust the scale of them. The skeleton of related animals are like that. They're just variations on each other. They're just stretched out and modifications of one another because we all come from a common ancestor. We all evolved from an animal that had all of these bones, and we are just modifications of that body plan. We are what happens when over millions of years of procreating, some of them grow to have more control over individual fingers, a little bit of control over individual fingers, none whatsoever, but the same bones. Does that make sense? And the fact that we have these same bones tells us that we're related. If we looked at a bird wing, would it have all those bones? Do bird wings have little bones coming down like this through their wings? Those are just feathers. It's an entirely different system. You've seen a chicken wing, right? Does a chicken wing look like that? No. So the fact that we have this very similar bone structure tells us these animals must be closely related to each other. Does that make sense? So let's say that in a sentence. Animals with very similar anatomy are presumed to be closely related. Now, is it possible that this could happen by accident sometimes? Like, could there be cases where two things evolved from a totally different ancestor and end up kind of looking the same?
Yeah, because if they evolved it, it's probably useful, right?
Exactly. So it absolutely can happen by accident. And this is not a perfect indication, but it's a guideline. It's one of the things that helps us understand. So when we look, and if you look at any mammal, you know, when we dissect the pig, if you take its forelimb apart, you're going to find exactly these bones. Whereas if you dissect the turtle and you take its forelimb apart, you're going to see it's similar. We're related to turtles, but it certainly doesn't have all the wrist bones that are the same, the exact same construction of the metacarpals beyond the wrist. They have different bones because they're not as closely related to us as the pig is. Our common ancestor with them is further back in the past, before all these bones had evolved. Now, if you look to the next page, we said this isn't always perfect. We look at the anatomy, but now science is more robust. We don't just have to look at anatomy, we can look at physiology. What's that word mean, physiology? I suppose I should say anatomy too. Anatomy is like the shape and structure of a body. Physiology, on the other hand, is, sorry, I didn't hear what you said. No, good thinking, but that's actually more anatomy as well. How it looks would be anatomy. Physiology is how it...
It's like the makeup, like how it works on the inside.
How it works, bingo. Yeah. A comparison would be like, you look at 3 trucks and you go like, oh, they have similar shapes. That's like the anatomy of it, right? Like, what's the shape? It has quarter panels. It's got a front grille. It's got a bed in the back. It's got 4 wheels. The engine's on the inside. But when we get to physiology, it's like, how's the engine work?
Yeah.
Oh, this truck is running on a V8. This one's running on a 4-cylinder. Those are very different structures and functions. Oh, this one has power steering. This one from the 20s is still using just, manual steering. That's the physiology, how it works. And with looking at species, that means looking at the cells, molecules, and processes. Oh, one S on molecules. I was already thinking about the word processes. Of that organism. Is anybody in here comfortable saying that they are diabetic or has somebody in their life who is diabetic? Anyone type 1 diabetes where they actually have to get the injection? Or know somebody like that? Does anyone know what you're injecting when you're getting an injection for diabetes? Insulin. And do you know what insulin is?
It's like a balances your blood sugar.
Very good. It balances your blood sugar. It's produced by, somebody said it. Well, we'll get there. So it's produced by your pancreas normally. Your pancreas has what we call endocrine function. It produces chemicals. And in the islets of Langerhans of the pancreas, you get the production of this chemical called insulin. And its job is to bring your blood sugar levels down. If there's too much sugar in your blood, insulin's job is to... Oh, I'm saying it backwards, aren't I? Give me a sec. I always get backwards.
Are you sure? I think you might have...
No, it's right. Down. It's down. And glucagon brings it up. I got it. All right, so its job is to lower your blood sugar level. Now, some people have a condition, a genetic condition we call type 1 diabetes, where their pancreases don't produce enough insulin. We are so similar to, and it was first discovered with dogs. For years, it was taken from, does anyone know?
I think it was like pigs or something.
Pigs,
I
yeah.
watched a documentary.
For years,
Yeah.
now it is mostly done synthetically. Now we mostly have actually genetically modified bacteria to make insulin. You can get it much cheaper, which makes it incredibly a piss off that it's more expensive than it's ever been to get insulin. But that's a different discussion. I shouldn't say piss off. It occurs to me that was inappropriate.
No, but
makes it more irritating. But listen, we are so similar to dogs and so similar to pigs that our physiology is similar enough that taking the insulin out of their pancreas and putting it in our body works. It does the job. We're closely related enough that we have that same process and we use that same molecule. Whereas if you tried to take something out of the pancreas of a lizard, it's not going to work. We aren't closely related enough to it. The insulin that regulates our blood sugar evolved after we had a common ancestor with lizards, but while we still had a common ancestor with pigs and dogs. A good example of this is that sometimes it surprises us. We said that we can look at anatomy and it tells us which are related. Here we have a horseshoe crab, a Dungeness crab, and a spider. Which 2 of these would you assume are most closely related?
The 2 crabs.
You would assume the 2 crabs. But in fact, when we looked at the physiology, and you might, if anything, even assume that these 2 are closely related because they kind of look similar, in practice, these are actually the closest relatives, which we know because of their physiology. We can actually tell from the enzymes that are produced in their body that these two are more closely related than the others. Physiology. So as our science gets more sophisticated, we sometimes find out that what appears to our eye to be more closely related isn't always true. And I think the dog example points to that too. You could easily look at a Chihuahua and a Great Dane and assume those are very different species. You could easily look at a horse and a zebra and say, oh, those look like they could be the same species. And so it takes a slightly more sophisticated level of understanding to be more accurate. And then we said yesterday, what is more accurate than just the shape of things? More accurate even than this, what is the most accurate way we currently have to tell if things are related or not?
Checking out their DNA.
Checking out their DNA. Because now, in 2022, we can read the schematic letter by letter by letter, code by code by code, and know exactly what the blueprint design, the genetic makeup of each organism is. And because we can do that, now it has gotten easier than ever to tell how closely related things are, because we can see how much of their DNA is shared, how much of their DNA is the same, and how much of their DNA is different. Does that make sense? If you went and looked up the blueprints of like a manufacturing company in Welland, probably all of the blueprints they make for things have a few things in common. And it wouldn't take you long, if you're a guy who looked at manufacturing blueprints, to be able to notice their stuff all the time, right? And be like, ooh, they always use this font, they always lay things out this way, this is always where they put that. And even if they're building different things, you'd be able to see the telltales, right? And then if one of their employees went off and started their own company, you'd probably see that their blueprint shared a lot of those similar traits, right? Yeah. Same idea here. The gold standard, the best thing we can look at is DNA. We can read the full blueprint, which of course is the DNA, of any species now. And I'm not going to bother writing that it's the best way to say how related two species are, because it says that here. But I will say this is a general rule. The more similar two species' DNA is, the more closely related they are. That's good. I'm going to get where I want to be. On Monday, we'll get drawn. You'll be glad to know Monday is not a note. So I'll let you copy that down. And while you copy that down, I want you to look just at a really simple example. This is a section of DNA from a bunch of different species. And this particular one, I'm trying to remember. I made this note myself. Did I put on here where it came from? Of course I didn't. I should have. That was bad of me. I do remember. This is looking at the DNA code to make the hemoglobin molecule. Do you know what hemoglobin is? It's in your blood, and it's what actually carries oxygen. Good. So your hemoglobin is actually what carries your oxygen around. And if you look, this is the piece of genetic code, a small section of it, that codes for how to make hemoglobin, how to make this molecule that's going to carry oxygen. Again, it's like a blueprint. This tells your cells how to make the molecule called hemoglobin that's going to carry oxygen for you. And if you look at a mouse and a rat, what do you notice about the section of genetic code for those two animals for this hemoglobin? They're spot on identical, not a single difference. If you compare that to a human, you'll notice that the rat and the human, the same, all of a sudden, boom, different and different. Just a little bit different. By the way, close enough that rat hemoglobin and human hemoglobin basically work the same, but they are slightly different, Difference between like a Dell power charger and an HP power charger. They may both work, but they'll look a little different. See a difference. Now look at a human, a pig, and a dog. What do we notice? Identical. Not a single difference. Chicken, pretty similar, but we're starting to see more changes, aren't we? Which makes sense. All of these are mammals. We get down to a chicken, we know we're less related to them. They're not a mammal, right? And yet, we're still quite similar, but more changes evident. A frog, lots of changes. Does that make sense? So we can compare different species and we can say the more similar their DNA, the more closely related they must be. And this is now the best way we have to differentiate species. Now keep in mind, with 1 million species on Earth and it costing about $10,000 still to run a genome, have we done this for every single species on Earth? Absolutely not. But with each passing year, more and more. Now, the last thing we're going to talk about is where we'll pick up on Monday, but we see a diagram like this. This is called a cladogram, or a phylogenetic tree. It's just another family tree. It's like the one we did at the beginning. And if you look at here, you can see every time there's a branching point, that is when some evolutionary change happened. That's when you had a branching, and all of a sudden you had a species becoming two species. Now, obviously, does this show every single branch that ever happened in the history of species on Earth? No, but it lets us compare these. And we can look and say, if we look, mammals were not very close, evolutionarily speaking, to birds. In fact, birds underwent changes all the way down the line to back here before they had a common ancestor with mammals. Does that make sense? We are evolutionarily pretty far apart from each other. We'll talk more about this diagram on Monday. Monday is just going to be a day where we do diagrams like this. But just really quickly, what are two really closely related things on this family tree? This phylogenetic tree. Yeah.
Birds and dinosaurs.
Good? Give me yours.
Ray-finned fish and amphibians.
Good. Ray-finned fish and amphibians are fairly close together. But even then, we actually have to go back pretty far. I would say closer than them, because they've been evolving separate from one another for quite some time. Whereas, what did you mention?
I said birds and dinosaurs.
Yeah, like if you look at birds and dinosaurs, they were actually on the same path not long ago at all. Does that make sense? If we imagine this being back in time, the branching for them only happened here, which is pretty recent. In fact, dinosaurs and birds lived together on Earth at the same time, but it wasn't too long before that there weren't dinosaurs on Earth or birds on Earth, but there was something on Earth that would eventually evolve into dinosaurs and would eventually evolve into birds. Does that make sense?
Yeah.
What is the next closest connection on here?
I don't know. I do, but I'm not.
The next closest connection. Well, if you go back in time, that would be this connection point here, right? And that's where dinosaurs and birds branched off from crocodiles. Does that make sense? All right. We're going to talk about this more on Monday. Don't do any of the homework on this sheet today. We're not done the note. Does that make sense? But what do I want you to do for homework? I want a mnemonic device. What else do I want done? Look here. Shh. I want everyone's eyes. What else do I want done? If you haven't already. A lot of you have, which is great. Some of you have not. Yep, that, but more importantly,
Get a binder.
safety. I want that safety modules finished. All right? And I want not handed in. No, I'll take a look at them, but I try to limit my paper intake, because once I start taking things from you, then if I don't get them back to you, then you don't have your notes, then how do you study? So I try to just make my way around and look and see who has done what, and then if I'm collecting things, I try to put on separate papers, so it's not stuff you'd want in your notes, which I'm usually pretty good about. Hey, can I ask, how was everyone's week 1? Does it feel a little bit back to normal? I have found that this feels more like a school year than the last couple did. I'm feeling good. I'll tell you, my voice. I got a sore throat. Right, yeah. Sorry? Sure. Do you want? Here, I can pull them up. I'll disconnect from here. Oh, sure. Show me.